Capacitor is going to be the topic of this lesson in my new General Physics playlist, which when complete will cover a full year of university algebra-based physics. Now, capacitors store charge, it's what they do. And in this lesson, we'll define capacitance, we'll talk about the potential energy stored in a capacitor, and then we'll talk about parallel plate capacitors and kind of their structure and design. We'll then finish this lesson off by talking about capacitors in circuits, when they're arranged both in series and in parallel. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now, I said in the introduction that capacitors store charge, it's what they do. And oftentimes their function is tantamount to them storing charge, and sometimes it's just a vehicle for them to produce some other function. So good examples would be like a defibrillator used to restart someone's heart whose heart is stopped. And ultimately, you're going to store charge on the two paddles. They're going to be a positive charge on one and a negative charge on the other. And when you touch the person's chest with both paddles, the hope is that current flows from one paddle to the other. That charge flows from one paddle to the other, right through their chest, right through their heart, and hopefully that electric impulse restarts their heart. Another example might be the keys in a keyboard. It turns out you've got a parallel plate capacitor set up kind of in the keys of this keyboard. And a parallel plate capacitor looks just like this. It's combined of two parallel plates hooked up in a circuit. One of those plates is going to accumulate a positive charge. One of the plates is going to accumulate a negative charge of exactly the same magnitude. And it turns out when you press the key down, you actually cause the plates to contact each other. And that discharge, that allows the flow of charge from one plate to the other. So, and that kind of gives the computer an indication of which key was pressed based on which capacitor was discharged, so to speak. So these capacitors can store charge, and then they can release that charge, which we call discharge. Now we should at this point define what's called capacitance. It's the main property of a capacitor, and it's just equal to Q over delta V, Q being the charge stored by that capacitor, and delta V is the potential difference put across that capacitor. And usually the source of that potential difference is some EMF source, electromotive force source, or battery, so to speak, as we'll see. Now if we rearrange this equation just a little bit, we can see that Q is equal to C delta V. So we'll find out that capacitance is going to be a constant for a given capacitor. So it's just governed by the capacitor design, as we'll see. So, but it's a constant. And so for that capacitor, we'll find out that Q is directly proportional to delta V. So if you double the EMF, if you will, double the potential difference across it with the battery, you will double the amount of charge stored by that capacitor as well. So directly proportional. You should also know that capacitance is measured in farads. So a new SI unit, the farad. And you can see from here that charge the SI unit is a coulomb. So, and potential difference, that SI unit is, let's get that right, the volt. And so a farad is a coulomb per volt. So, but you definitely want to remember that capacitance is measured in farads as the SI unit. All right, so in addition to the definition for capacitance here, so we can also talk about the potential energy stored in a capacitor when you're storing up that excess charge. And so ultimately, if we take a look at the design of this parallel plate capacitor over here, so ultimately you're going to have current flowing from one side to the other. And that's going to leave one of these again with excess positive charge, and it's going to leave the other plate with excess negative charge. We'll come back to that in just a second, but having such a concentration of positive charges on one plate and negative charges on the other plate, that's going to be a situation that has a lot of stored potential energy. And so we've got an equation for this stored potential energy, and it turns out my personal favorite is 1/2 C delta V squared. So because it looks a lot like, say, kinetic energy of 1/2 mv squared. Obviously, the formula looks somewhat similar, but the terms are totally different. It is pure coincidence. So, but we can look at two other forms of the same equation here. If we take and replace C with Q over delta V, then we're going to have Q, and then one of the delta V's here is going to cancel. So you're going to be left with 1/2 Q times delta V, another way of looking at it there as well. So, but you can take this one here and replace delta V here. You can see that delta V would equal Q over C. So, and you'd be left with 1/2 Q squared over C, which sometimes we just put the 1/2 kind of in the denominator there and write it as q squared over 2c. Any one of these three, they're all mathematically interdependent. They all lead you to exactly the same result for a given capacitor experiencing a given potential difference. So let's go back and take another look at this parallel plate capacitor now. And so if we take a look at this parallel plate capacitor, the most common design that you're going to encounter, and probably the only capacitor design you'll encounter in this class. So we're going to hook this up to what we call an EMF source or battery, and this is the lovely symbol we use for batteries and circuits, and we'll see some more symbols here in the next part of this lesson. So, but the two lines, one, they're not the same length. We'll find out that capacitor is going to be represented by two lines of the same length in just a little bit, but when they're of unequal lengths here, that represents a battery. The longer line represents the positive terminal of the battery. The shorter line represents the negative terminal of the battery. So that's how that works. And what a battery ultimately does, you can kind of think of it as a pump for charge. And it's there to raise the potential energy of the charge flowing throughout that circuit so that it can fall downhill. So you can kind of think of it as like pumping water uphill so it can fall back down, like in a fountain or something like this, where you got a water feature and you have to pump the water to the top of the feature so that it can fall back down, and then it pumps back up so that it can fall back down. And so same kind of thing here. That's the job of the battery. It's to pump those electrons to the way they have high potential energy so that they can fall through that circuit, so to speak. Now we know that the actual current flowing through a wire is actually electrons. We know this now. We didn't know this a couple hundred years ago. And a lot of the physics was developed assuming that it was positive charges that were flowing. And the idea is this: whether you have positive charges flowing from one side to another or negative charges flowing in the exact opposite direction, those produce exactly the same result. An excess of positive charges on one side, excess of negative charges on the other side. And they didn't know which was actually happening or if it was both. So they just picked that it was the flow of positive charges. Well, we now know that positive charges are kind of anchored in the nucleus, and it's actually the flow of electrons, negative charges throughout the wire. So unfortunately, though, most of physics has been taught for a couple hundred years with the guise that it's the flow of positive charges, and so we still teach it that way. We call this conventional current. We know that real current is the flow of electrons through a wire typically, but conventional current is going to kind of be this, what I'm going to call the imaginary flow of positive charges, and much of the physics is still taught that way. Sorry to tell you. All right, so if we take a look at this conventional current, so you typically have it flowing from negative to positive here. So in this case, we're going to have positive charges kind of flowing in this direction, leaving you excess positive charges on the positive plate there. So, but we have to complete the circuit here. The flow of positive charges is going to, this thing is really going to pump, and it's pumping these imaginary positive charges in a single direction throughout the circuit. So, and in this case, those excess positive charges, ultimately, their original the original place where they might have come from would have been ultimately from the opposite plate. Now, it turns out that the positive charges of this plate are probably not the same ones that left this plate. So it turns out the wire is full of charge that is mobile and stuff like that. So, but because positive charges have left this other plate, it leaves it now with a net negative charge. So, and the charge magnitude on both these plates is exactly the same. So if this had positive 10 microcoulombs, then this would have negative 10 microcoulombs of charge, always the same. All right, and how big that charge becomes depends, one, on the capacitance of the capacitor, but also then on the EMF, the potential difference of your battery. All right, now it turns out for your parallel plate capacitor, so your capacitance is equal to epsilon naught times the area of the plates divided by the distance of separation. So this is our lovely equation. Now, epsilon naught we saw in the last chapter. It was the permittivity of free space. It still has that same value of 8.85 times 10 to the minus 12. So, but area here is the area of the plates. And as long as they're nice square plates, you can find the area of a square as just side squared, or if the rectangular, length times width, so on and so forth. And in this case, the plates are designed to have exactly the same area typically. So it's not like you have to find the two areas and add them together. It's the area of either plate since they have the same area. All right, and then the distance of separation is going to be this distance of separation between the plates. So, and if you look at this, this kind of makes sense. So if the job of these plates is to store charge, well, then the bigger area they have, the more charge they can store. And the more charge they can store, the higher the capacitance. And so it makes perfect sense that the capacitance is directly proportional to the area of the plates. But the capacitance is inversely proportional to the distance of separation. And so the idea is that if you take these two plates and you put one in China and one in Australia, they're separated by 1,000 or a couple thousand miles or something like this, and one plate doesn't know the other plate exists, and they're not going to really have any charge accumulation on them as well. But the closer you can put them, so the greater the charge accumulation on those plates is going to result. That's kind of the deal. If you put them infinitely far apart, one plate doesn't really know the other one exists. And so at least that's how I like to think about it. So, and therefore capacitance is inversely proportional to the distance of separation. You want to make that distance as small as possible to get the greatest capacitance possible for your capacitor design. Okay, so it turns out we can do one other thing with this lovely, we'll talk about one other thing real quick. So with your parallel plate capacitor, as long as you're not too near the edges, so it turns out you can look at the electric field flowing from positive to negative here, and it turns out it's constant everywhere. So if you look at all these positive charges exerting at any point in space down here, and all these negative charges are then going to have the electric field pointing down towards them. So when it turns out at any point in between these two plates, the electric field is roughly constant. Now as you get out towards the edges, that's not true, because you're out towards the edge here, you might not have as many positive charges off to the left as you do onto the right and stuff like that, and so it's not quite so constant. But anywhere towards the interior, it's going to be constant, and so we like to just envision it as being constant anywhere we're likely to look in between those plates. So, and we learned an equation for this, that delta V equals ED here. We kind of alluded to the fact that we might use this a little more in this lesson than we did in the last one here. So if you take the potential difference again across these plates of the capacitor, so and then divide it by that distance of separation, you can actually calculate the electric field that's constant everywhere between there. Now we have one more thing to talk about. So in this case, we're considering a situation where the space between the plates is empty. And by empty here, I mean one of two things. It could be in a vacuum, or it could just have air filling it. In either case, it doesn't make much of a difference, and this equation applies. So, but it turns out you can actually fill that space with what we call a dielectric. And it's usually some sort of polarizable material, or polar material that can align with this electric field, which is going to enhance the amount of charge that can be stored between those two plates. And so in such a case, we get this kappa, this dielectric material, times epsilon naught times A over D. And if I kind of put this in parentheses, you can kind of see what's going on here. It's really just amplifying the capacitance by some constant factor kappa, which we call the dielectric constant. And for different substances, it's different values and things of this sort. But typical values for kappa are all greater than 1. It's always going to make the capacitance go higher when you put a dielectric in there. So, and basically, if you have a dielectric of 2, that just doubled the capacitance compared to air or vacuum. So, and then when I say air or vacuum, it turns out for a vacuum, that dielectric constant is exactly 1.000. For air, it's like 1.006, which is pretty much darn close to 1. So we just consider air and vacuum effectively to be the same as far as capacitance, and just use this equation. But put a dielectric in there, and whatever that dielectric value is, that's the factor by which it amplifies the capacitance. Again, a dielectric constant of 2.0 doubles the capacitance. 3.0 triples the capacitance. 10, amplifies the capacitance by a factor of 10. Cool. And from here, I think we're ready to do some plug-in and chug-in. So the first question we're going to take a look at here is a 3-part question. It reads, a parallel plate capacitor with air between its plates stores a charge of 24 microcoulombs when charged with a 12-volt battery. First question, what is its capacitance? Okay, and this is just simple plug and chug with our definition of capacitance here. So C equals Q over delta V. And in this case, the Q is given as 24 microcoulombs. So, and then delta V is given as a 12-volt battery. Okay, now one thing to note, you might be like, hey Chad, you probably should put this in as 24 times 10 to the negative 6 coulombs. And you could, and we'll find out that the result doesn't really matter if we do or don't, sort of. All right, if we do the math here though, 24 divided by 12 is 2. In this case with 2 sig figs, that's 2.0. And in this case, when you do coulombs over volts, you get farads. When you do microcoulombs over volts, you get microfarads. So, and it turns out, just like a coulomb of charge is a phenomenal amount of charge, you're not likely to see a full coulomb of charge. You're much more likely to see like microcoulombs, nanocoulombs, picocoulombs. Same thing with capacitors. You're much more likely to see microfarads, nanofarads, picofarads than plain old farads. Now, it wouldn't be wrong, but again, a lot of the questions you're going to do are going to have, like, say, multiple choice answers reported, not necessarily just farads, but much more likely to see in microfarads, nanofarads, picofarads. And so in this case, if you plug in your potential difference in plain old volts, but you use your charge either in microcoulombs or nanocoulombs or picocoulombs, your capacitance in farads will come out with the same prefix. So in this case with microcoulombs, it comes out as microfarads. And you can see why that is. This is really 24 times 10 to the negative 6 coulombs, which is why this would have come out to 2.0 times 10 to the negative 6 farads, which is 2.0 microfarads. All right, so there's our capacitance. That's the first question. Second part of this question says how much potential energy is stored by this charged capacitor. So, and in this case, I erased a couple of the formulas for potential energy stored. They're in my way, but any one of them could work here. In this case, for me, truth be told, it looks a little easier if we use that second formula of 1/2 Q delta V. Now here's the truth. This is the only one of the three formulas I actually have memorized in my head. 1/2 C delta V squared, because again, it looks a lot like 1/2 mv squared, and it makes it easy for me to remember. So, but any one of those three is possibly used. And if you're given an equation sheet, you can pick which one you want to use. If there's one that's going to make the math a little easier, like this one, I don't have to square anything. And when you square things, the numbers get big, and I might have to pull my calculator out, so on and so forth. But this one doesn't look too bad, so that's the one I'm going to choose to use here. And so, in this case, we got 1/2. So, in the charge, we already stored given in the question, 24 microcoulombs. In this case, I will write it as 24 times 10 to the negative 6 coulombs. We'll see why in a second. And in this case, times delta V, and delta V was once again given as 12 volts. So now, again, we could have used this other formula here, which has capacitance in it, because we solved for it. But had we been asked for the potential energy from the get-go without having answered that first question of finding the capacitance, this might have been the easiest route to go because we could plug in the numbers that were given in the question. Whether we use 1/2 C delta V squared or Q squared over 2C, we would have had to solve for the capacitance first to get there. So, but any one of those three formulas will lead us to exactly the same solution here. In this case, we can multiply this in any order. I like smaller numbers, so I'm going to do 1/2 times 24 to get 12. 12 times 12 is 144, and then times that 10 to the negative 6. And the potential energy stored is 144 times 10 to the negative 6 joules. Now, once again, if we used 1/2 C delta V squared, it would have led us to the same result. We would have had 1/2 and then times 2.0 times 10 to the negative 6 farads, and then times 12 squared. Well, again, 12 squared is 144. 1/2 times 2 is 1, and you still end up with 144, and again, times that 10 to the negative 6. Now, this is not proper scientific notation. If you reduced it down, you'd get potential energy equals 1.44, move that over a couple places, and then times 10 to the negative 4 joules. And in this case, we're going to round it to 2 sig figs and just make it 1.4 times 10 to the negative 4 joules. Now, you might be like, well, Chad, why didn't we do what we did up here and just leave it in micro and go micro? For whatever reason, with energy, you often don't necessarily see it that way. And so, could you call this 144 microjoules? You could, and it would be technically correct, but if you're given a multiple choice test, you're probably not going to see it expressed that way. So I'm going to try and express it in the most likely way you're going to, and in this case, again, 1.4 times 10 to the negative 4 joules expressed in 2 sig figs. All right, next part of the question, what would its capacitance be if the air between the plates were replaced with polyphenylene sulfide and the dielectric constant of 3.0 is given in parentheses? So in this case, we already solved for the capacitance. Another way you can rewrite this formula is you can realize that epsilon naught A over D, that's just the capacitance either in a vacuum or air here. And so sometimes you'll see this written as C prime equals kappa times C, where that C is the original capacitance in air or vacuum. So in this case, we could just then take that kappa of 3.0, that dielectric constant, and then times the original capacitance of 2.0 microfarads. And just like we said, if you've got a dielectric of 3, that is going to triple the capacitance relative to vacuum or air. And so in this case, that's going to get us the 6.0 microfarads. For the rest of this lesson, we're going to be dealing with capacitors in circuits. And you got to understand some of the symbols we use in circuit diagrams. And so one of them we already kind of alluded to, and that's the symbols for a battery or an EMF source. And you got two parallel lines, one longer, one shorter. And the longer line represents the positive terminal, the shorter line represents the negative terminal. So If you have two parallel lines, though, of the same length, that's the symbol we use for a capacitor. So, and it kind of, to mimic the parallel plates of a parallel plate capacitor. But even if it's just some other type of capacitor, that's the generic symbol we use for any capacitor, two parallel lines of the same length. Now, we're not going to see it and use it really in this lesson, but I figure it's a good time to introduce this, so we will see it in the next chapter. So where the symbol for a resistor looks like so. So, and it turns out using this symbol is actually quite convenient. Let me put a few of these in a row here in a single circuit. And that'll help us define something else here. So it turns out when you've got multiple circuit elements, and in this case we've talked about capacitors, we've talked about resistors, and we've got batteries. These are your circuit elements, and specifically we want to focus on the capacitors and resistors. So, and when you put them in the same circuit, it turns out there's two fundamental ways in which they can be arranged, and we call those series and parallel. So I'm going to use this kind of example. So it turns out the house my mom grew up in way back in the day, she came from a rather poor family, and they had a house that was behind the times as it was. So, but if you went into a house, say, 100 years ago, it might have the same setup as my mom's old house. And the way it worked, they had 9 light bulbs in the house, and it turns out a light bulb functions as a resistor. And as current flows through that light bulb, it flows through the tungsten filament, it gives off light as well as heat. And it's the light part that allows it to function as a light bulb. And so in this case, we like to view conventional current as flowing off that positive terminal. So, and it keeps flowing around the circuit till it gets back to the negative terminal. And the whole job of the battery is to raise its potential energy. And it's because that potential energy is going to fall all the way around the circuit. And so it raises it again so it can fall all the way around the circuit yet again. Here's the problem though. If any one of these light bulbs, if that tungsten filament were to break, the current can't jump the gap and it has no way to flow anymore. And so not only is this light bulb dead, the one that actually had the tungsten filament go out, but you're not going to get any current to flow through either of these either. And so all of a sudden, one light bulb going out causes all the light bulbs in the house to go out. This is how the Christmas lights used to work as well. So if you're as old as I am, you can remember Christmas lights being the biggest pain in the butt. When one bulb went out, the whole strand went out. Same kind of thing. And so what my grandpa would have to go do is he'd have to go sequentially replacing that light bulb, see if it fixes the circuit. Replace that light bulb, see if it fixes the circuit. Replace that light bulb, see if it fixes the circuit. Potentially through all 9 until finally he finds the one that's broken, replaces it, and the whole circuit is restored. Well, we don't design circuits like this anymore. So it turns out we put multiple pathways in our circuits. Let's put that resistor back fixed again. We put multiple pathways in our circuit, and that way if there's a break in any one of these resistors in this case, so the current can still flow around through some of these alternate pathways as well. And so if I break this circuit, oh, no big deal. I can still flow around right here. So, and at least this light bulb's not going to go out. Well, it turns out we'd even set it up with more parallel pathways so that even this one wouldn't go out as well. So everything's arranged in parallel. So some distinct advantages to doing it that way. So now we've got to distinguish between series and parallel proper. So in the way this works, if you've got a single pathway on which the circuit elements are arranged, that is in series. And that's this first one we've got right here. So between these two elements, there's a single pathway to get from one to the other. So that's how it works. And it's easier to actually define series when you see the contrast with elements that are arranged in parallel. When you've got a parallel arrangement, you can identify what are called junctions, where you have wires flowing in more than 2 directions from those junctions. And what you're going to find out is that you've got multiple pathways to get from one junction to the other. And so as current wants to flow around this way, once it hits this junction, to get back to the negative terminal, it has 2 options. It can flow through this pathway, it can flow through this pathway. And those are alternate pathways from this junction to this one. And the capacitor, one capacitor is on one pathway, the other capacitor is on the other pathway. They're on parallel pathways, and we'd say they're arranged in parallel. Now, it's a little bit tricky here because with capacitors, current doesn't actually flow through a capacitor. There's an actual gap right there. If we were talking about resistors, we could say that, the current does flow through it. It turns out when you're charging up capacitors, there is a flow of current in the circuit, but still no current actually flows across the gap. So, but you can kind of see how we define series and parallel nevertheless. Now, it turns out in addition to having capacitors in this case, arranged in series or parallel, it's often also convenient to envision a simpler circuit. So it turns out for any combination of capacitors or resistors, as we'll see in the next chapter, you can actually look at them all as kind of functioning as a single capacitor, in this case, in a very simple circuit. So, and it turns out having these two capacitors arranged in series would be no different than having a capacitor of a different magnitude, just one of them, in the circuit. So, and it turns out you could actually have a circuit that functioned exactly the same by choosing a capacitor of just the right magnitude. Okay, well, how do you find that special magnitude at equivalent resistance? Well, it turns out, in the case of when they're in series, they add as reciprocals. That's going to be 1 over C1 plus 1 over C2 plus dot, 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 if you have more than two of them arranged in series. Now, if you have them arranged in parallel, it turns out this is the easier situation. You're just going to have the equivalent equivalent capacitance equal to the sum of the individual capacitances, and it's really easy to do. And so in parallel, that's the gift right here as far as capacitors go. We'll find out with resistors, it's exact opposite of which one's the gift. But when you can just simply add them together. So here C1 plus C2, 6 microfarads plus 3 microfarads, is going to get us an equivalent capacitance of 9 microfarads. Life is good. And so we're going to answer a couple questions involving these two sets here. And the first one was, what is the equivalent capacitance of each circuit? Well, we just found it for that one. It was easy, 9 microfarads. The second question is, what is the charge stored on each capacitor in the circuit? And so from here, we can work ourselves backwards and use our definition of capacitance to go back and use the delta V, the C, to find the Q for this equivalent capacitor. But we'll come back to that in just a little bit. All right, so for this one, it's a little more work to find this equivalent capacitance. So we're actually going to have to work out the math. And so this 1 over the equivalent capacitance is going to equal 1 over C1, so 1 over 6 microfarads plus 1 over 3 microfarads. And so we got to go down this whole road of finding a common denominator and stuff like this. And so in this case, the lowest common denominator is going to be 6. And we could figure out what that lowest common denominator, or how to get there, by multiplying the second term by 2 over 2, leaving the first term alone. It already has a denominator of 6. And so we'd have 1 over 6 plus 2 over 6 would equal 3 over 6. And so we'd have 1 over the equivalent capacitance equals 3 over 6. And to solve for the equivalent capacitance, you just invert both sides. And so you end up with the equivalent capacitance equal to 6 over 3, or simply 2 microfarads. Okay, not so bad. So one other approach we could take, and this only works if you only have two capacitors in series like this, but if you have only two capacitors in series, there's a little trick. Because sometimes identifying the lowest common denominator is a pain in the butt. Now, it's not so bad with 6 and 3. That's pretty easy to see. But what if you had, like, 37 and 42 and, I don't think you're going to see a problem like that, but just imagine trying to find that lowest common denominator. Well, instead of finding the lowest common denominator, sometimes it's just easiest to find the easiest common denominator. And again, this trick is only a trick for when there's just two capacitors. If you have 3 or 4, good luck. You got to figure out how to do this. But if you have just two capacitors, it turns out a common denominator you can always rely on is just simply multiplying the denominators together. And 6 times 3 is 18. And it's not the lowest common denominator in this case, but it's an easy one to mindlessly find. All right. If I wanted to get to that lowest common denominator of 18, I'd have to multiply this first term by 3 over 3 and the second one by 6 over 6. And if you look at what this ultimately comes down to, so you'd end up with 1 over the equivalent capacitance equals 3 plus 6 all over 3 times 6. So you'd have 3 over 18 plus 6 over 18, which is 3 plus 6 over 18. Well, if you rearrange this and go back then and flip both sides over, and notice instead of writing 18, I'm going to write this as 3 times 6. That's where the 18 come from. And so if we just solve for that equivalent capacitance, we could get 3 times 6 over 3 plus 6. And you'd get 18 over 9, and you'd get 2 microfarads. And it works out the same way. Now, if you want to oh, Chad, then I got to remember which one's on top. Am I multiplying on top or adding on top or something like this? Well, you can work the units out, because here you'd have microfarads times microfarads, which would be microfarads squared. And on the bottom, you'd microfarads plus microfarads, which is simply microfarads. And you end up with microfarads squared over microfarads, which gives you microfarads. If you did it the opposite, you'd end up with units of 1 over microfarads, and it wouldn't work out. One way to kind of remember if you struggle to get that formula. But again, you don't actually have to use this. It was just another way of coming out with that 2 microfarads if finding the lowest common denominator for two capacitors in series is a pain in the butt. Okay, So let's go back to this for a second. So we found the equivalent capacitance for both of these. And again, let's write this one out up here. It was 2 microfarads. So, and we can look at this equivalent capacitance scenario here for this single simple circuit, if you will. And we can look at the delta V and the equivalent capacitance and very quickly find the total charge stored by that equivalent imaginary capacitor. Now let's do that for a second. So in this case, we rearrange this just Q equals C delta V. So in this case, that's going to be C was 2 microfarads, delta V is 12 volts, and we can see this is going to work out to give us 24, and I'm going to call this times 10 to the negative 6, let's leave this micro, my bad, microcoulombs. Same thing over here. So in this case, we're going to have Q equals C delta V, which was 9 microfarads times delta V of 12 volts. And 9 times 12 is going to get us 108 microcoulombs. Okay, so what does this ultimately mean? Because this is the total charge on that equivalent capacitance circuit. What does this ultimately mean? Well, here's the deal. What it ultimately means on a series circuit, the Q you solve for here is not just the Q stored on the equivalent capacitor if you had it, so 24 microcoulombs, it's the Q stored on each of the capacitors as well. Not the case when they're arranged in parallel though. When they're arranged in parallel, the total Q we just solved for right here on the equivalent capacitance, turns out that is the total, the sum total of the charge stored on either of these. And we'll figure out what those come out to in just a little bit here. In fact, why don't we figure it out real quick? So in this case, Q is equal to C delta V. So coming back here, so Q is equal to C delta V. And again, delta V is the same for both of these. It turns out when you've got parallel pathways, so between this point and this point, no matter what pathway you take, the potential drop is exactly the same. So for any two elements that are on a parallel pathway, so as long as they're the only element on those pathways, the delta V is exactly the same. Okay, so if the delta V is exactly the same, so then Q is going to be proportional to C in that case. Well, this C is double this one, which means the Q is going to be double for this one as compared to this one as well. It's a 2-to-1 ratio of capacitances. It's going to come out to be a 2-to-1 ratio of charge being stored as well. And so what we want to do here is take that 108 and break it up into 3 parts. 2 parts for one, 1 part to the other, and that way we get the 2-to-1 ratio. So let's pull out our calculator, let it do the heavy lifting for us. So we'll take that 108 and divide by 3, and we get 36. So that's going to make it, for the one that has 2 parts, it gets 2 times 36, so Q equals 72 microcoulombs, whereas the 3 microfarads only gets 1 part, so that's going to be Q equal to 36 microcoulombs. A 2-to-1 ratio that adds up to exactly 108. So the other way you could have figured this out, you could have said, in this case, you got 108 total, and this is going to get 6 out of a total of 9 microfarads, if you will, 6/9 of that 108. And if you take 6/9 of 108, you get 72. Whereas this is only going to get 3/9 of 108, which comes out to 36. The other way you could have looked at that. All right, going back to this one, when you have them arranged in series, the way this works, so this battery is first turned on, so to speak, you're going to get the imaginary flow of positive charge. So from the positive terminal to the first positive plate, that's going to make it positively charged. Because it's positively charged, positive charges are going to be repelled on the plate right next to it, and that's going to cause positive charges to flow away from it onto the first plate of the next capacitor, causing it to have exactly the same positive charge of the first one. So, but not only did we give this guy a positive charge and then him the same positive charge, because that positive charge came from that number of positive charges leaving the second plate, that's why it ends up with a negative charge. And the same thing's going to happen here as an equal number of positive charges leave this plate to return back to the negative terminal of the battery. So here's the deal. So when you've got 2 capacitors in series, they will always have the same charge. So, and when you give the charge on these capacitors, by the way, the positive plate and the negative plate will always have the same magnitude of charge, just one positive and one negative. And it is either magnitude that is defined as the charge of that capacitor. And so in this case, we said that the total charge being stored by the equivalent capacitance was 24 microcoulombs, and it was 24 microcoulombs for both of these as well. That's the way it works in series. Whatever the Q of the equivalent capacitance is also the Q of either one of those capacitors as well. Doesn't work that way here. So here, these don't have to have the same charge. It's the potential drop, the delta V, that's the same for both of these in parallel. The charge does not have to be the same, so you can't set them equal, and they're not equal to this total either. This total is just the sum of the two instead. And the question we want to ask ourselves is, why did the math work out different with these? And we've explained why these have the same charge and why these have the same delta V, and that's how we're going to actually explain why for the series capacitors we added them as reciprocals to get the equivalent capacitance, whereas for the parallel capacitors we added them straight up, which was much easier. Well, why did that work out the way it did? Well, it really is a derivative of the fact that here they have the same charge for series, whereas here they have the same delta V for parallel. Let's take a look. Okay, so going back here for series, the Q is the same for both capacitors. And I don't want to start with what's the same, I actually want to start with what's different. So in this case, it's the delta V that's going to be the different between these two. And again, obviously they have different capacitances, but again, it's either Q or delta V that's going to be the same for either one of these, and I want to start with what's different. And here it's delta V that's different for them being in series. And so the delta V across both of them combined is just the potential difference across one plus the potential difference across the other. Now in parallel, it's the opposite though. So now it's the delta V's that are same, it's the Q, the charge being stored on each, that is technically usually going to be different. And so that's what I want to start with. Q total is equal to Q1 plus Q2. It turns out if you try to do this the other way around, if you try to start off with what's the same, well, in this case over here, if I started with delta V, well, the delta V of the equivalent circuit and the delta V of either pathway is exactly the same, and I just have delta V equals delta V equals delta V, and that's not a very useful equation. Same thing over here, it's the charge that's the same, whether it's the charge on the equivalent or the charge on either capacitor, and if I just said Q equals Q equals Q, it's not super helpful. So that's why we started where we started, and now we want to take this to the next step. So if we go back over here to Q equals Q1 plus Q2, that might be easier to demonstrate first, because Q is going to equal C times delta V. And I'm going to substitute that right in. So for the total, that's going to be the equivalent capacitance times delta V. Q1 is going to be C1 times delta V, and Q2 is going to be C2 times delta V. And notice I'm not writing like delta V1 and delta V2 because delta V on any pathway as well as the total is exactly the same. So it's just delta V. There's no reason to simplify it any further. They're all equal. Because they're all equal, I can divide the whole equation by delta V. And they just cancel, and notice I'm just going to be left with C equivalent equals C1 plus C2, which is why they're just purely additive. Over here when they're in series though, so now we want to substitute delta V, and if you rearrange this a little bit, move C down and delta V up, and we're going to get delta V equals Q over C. And we'll substitute that in here, and so here we're going to have Q over C equivalent, and this is the total Q. So, and I say that tongue-in-cheek just a little bit. So delta V1 is going to be Q1 over C1, and delta V2 is going to be Q2 over C2. And you might be like, well, Chad, you just told me over here. Exactly right. So notice Q total, Q1 and Q2, it's all the same Q when they're in series. There's no reason to distinguish them. And as a result, then, this equation gets very simple in a hurry. I can just divide the Q out of the whole thing. And I'm just left with 1 over the equivalent capacitance equals 1 over C1 plus 1 over C2. That's ultimately why they're being added as reciprocals. Let's now carry this to a little more complicated problem. So the next question we're going to study in this lesson involves this lovely diagram here with many capacitors in it. And the question says, calculate the equivalent capacitance of the following circuit. Calculate the charge stored on each of the 4 capacitors. So multiple things we need to solve for here. And in this case, we've got so many capacitors that it's not going to be able to simplify this diagram in a single step. It is a multi-step process here. So if we take a look at this here, though, we can identify a couple things. So I can see we've got just a single battery here, 12 volts. And then from this junction to this junction, I've got 2 alternate pathways I can take. And so the circuit elements on either of those pathways must be arranged in parallel to each other. Same thing if I look at this junction right here to this junction right here. And again, there's two pathways to go from one junction to the next. And the circuit elements arranged on either of those pathways must also be in parallel. And that's what I can define. And so I can simplify this diagram down a single step here. As if these two were a single equivalent capacitance and these two were a single equivalent capacitance, and that's what we're going to do. And so in this case we've got 12 volts, and then we're going to have an equivalent capacitance here and an equivalent capacitance here. So what's nice is these are in parallel, and if you recall, when they're in parallel we simply can just add them together to get the equivalent capacitance. And so in this case 4 microfarads plus 2 microfarads is 6 microfarads. And 9 microfarads plus 3 microfarads is 12 microfarads, and that's not so bad. And now if we look at these equivalent capacitors, if you will, how are they arranged? Well, they're on the same single pathway of the circuit. They're in series. And so how do we add them together? As reciprocals to finally get a circuit that has a single equivalent capacitance in it. And there's a couple different things we could do. Since there's just two of them, you might remember we can just do 6 times 12 over 6 plus 12. And 6 times 12 is 72, and 6 plus 12 is 18, and 72 divided by 18 is exactly 4. So, or you could write it out, right? You could say 1 over the equivalent capacitance equal to 1 over 6 plus 1 over 12. And in this case, lowest common denominator would be 12, so you can multiply this first term by 2 over 2, and you'd end up with 2 over 12 plus 1 over 12 is 3 over 12, and then you'd flip it over to get the equivalent capacitance. It'd be 12 over 3, which is 4. But no matter how you slice it, we're going to get an equivalent capacitance here of 4 microfarads, and we still have over here a 12-volt battery. Let's draw that a little bigger on the long line. All right. So we've answered question number 1. What is the overall equivalent capacitance? Now we want to go back and find the charge stored on all 4 of these capacitors. And the way you do this is you work backwards. We're first going to find, well, if this was the equivalent capacitor of the circuit, what charge would it store? And then we'd say, well, then if these were really the equivalent capacitors that combined to form him, what charge would they each store? And then we go back from each of these to get the 4 of these and what charge they store. So that's kind of how this is going to work. Now, what we have to remember here is that when we go to solve for this equivalent, when we get to the charge on this guy, it's also going to be the charge on the 2 that are in series that make it up. If you recall, the charge stored on capacitors in series is the same, and it's the same as the equivalent charge, or the charge being stored by the equivalent capacitor they comprise as well. And so in this case, we'll go back and solve for Q and say that Q is equal to C delta V. And so in this case, the C is the equivalent capacitance of 4 microfarads times the delta V of 12 volts. And we see that's going to come out to 48 microcoulombs. And so right here, Q equals 48 microcoulombs. And again, for the 2 equivalent capacitors that are comprise it that are in series together, they also are going to have a Q, no calculation needed here, of 48 microcoulombs. All right, but now we got to go one step backwards and go back to now these 2 in parallel. And again, when you're dealing with parallel, we'll start with the lower one that's a total of 48. It's a total of 48 between the 2. So the Q stored on this 9 microfarad capacitor and the Q stored on the 3 microfarad capacitor adds up to a total of 48. So that's going to be the way that works. How do we figure it out? Well, a couple different ways. You could look at this and say, oh, it's 9 microfarads versus 3 microfarads. That's a 3-to-1 ratio. And recall that they're going to have the same delta V across them. That's exactly the same. What's going to be different, though, is the charge being stored on them, since their capacitance is different. And the charge is proportional to the capacitance. So since the capacitance here is 3 times bigger than this one, then the charge it stores is going to be 3 times bigger when they're in parallel as well. And so I could look at that and say 3 times bigger means a 3-to-1 ratio, which means I'd want to break up that 48 microcoulomb, my 48 microcoulombs into 4 parts. And if there's 4 equal parts of 48, that's 12 each. And the part that's 1 would be 12 microcoulombs. The part that's 3 parts would be 36. And so here we can say that this is going to have a Q of 36 microcoulombs. This is going to have a Q of 12 microcoulombs and adds up to 48, and it's a 3-to-1 ratio. The other way you could have done this, if you don't like that whole 3-to-1 ratio thing, this always works as well. You can take that total of 48 microcoulombs and you can multiply it either by 9 over 9 plus 3 or by 3 over 9 plus 3. So 9 over the 9 plus 3, and just another way of finding it, in a 3-to-1 ratio, so the 3 represents 3/4 of the total, whereas the 1 represents 1/4 of the total. And here's just a way of finding that 3/4 or 1/4, just using the exact numbers and not trying to simplify the ratio at all. And so 9 out of 9 plus 3 is 3/4 of the 48. 3 out of 9 plus 3 is 1/4 of the 48 between the two. And we can do the exact similar calculation here with the 4-to-2 ratio. And a 4-to-2 ratio reduces down to a 2-to-1 ratio, which means now I want to divide up that 48 coulombs total between the two when they're in parallel into 3 parts. And when you divide 48 by 3, you're going to get 16. And so the side that represents just one of the 3 parts is going to have a Q of 16 microcoulombs. The other side that gets 2 parts is going to be a total of 32, 2 times that, so microcoulombs, and 32 plus 16 adds up to 48. And once again, you could have done the same thing. You could have said, I'm going to take that 48 microcoulombs, and in one case, I'm going to add it, or multiply it by 4 over 4 plus 2. Whoop, 4 plus 2 is 6. 4 over 4 plus 2, and in the other case, I'm going to multiply it by 2 over 4 plus 2. And again, it's just a way of finding that when you got that 2-to-1 ratio, the thing that has 2 parts represents 2/3 of the total, whereas the part that has 1 is 1/3 of the total. And that's a way of finding that 2/3, 4 out of 6 is 2/3, or 2 out of 6 is 1/3 between these two. But that's how we can get the charge of all 4 of the capacitors there. And again, we had to simplify it down to get the equivalent capacitance, and then start figuring out going backwards the charge on each of the equivalent capacitors before we could find it on each individual capacitor in the original drawing. If you found this lesson helpful, consider giving it a like. Happy studying.